Just as variables were the critical idea to understand in the first set of exercises, functions are the critical idea to understand from this second set of exercises. The additional Python commands that we are going to introduce in these later exercises will make your codes shorter and thus better. Understanding these commands is less critical than understanding functions, however. In fact, really, you should be able to write longer codes that do most of what is going to be covered in these next few exercises. Without further ado then, let's dive into a recap of what we have learned about computer programming thus far. We have seen how variables are labeled addresses in memory, and we have talked about how these labeled addresses have a state and how we can store a value in the state of a variable. Thus far, we have introduced two types of variables. Variables for holding scalars, such as a here, which has been set equal to 4. And we've also introduced numpy arrays, which can be used to store multiple scalars in an ordered list. In addition to studying variables, we have also studied functions, and we have discussed how functions are used to change the state of variables. We have seen that a function is essentially a series of instructions that is performed when the function is called. As shown schematically here, variables can be passed to functions. The function will then do its thing and will return one or multiple values, which can be stored in the state of a new variable or variables. Thus far, the functions we have focused on take scalar values in input as shown here and operate upon them. The question we would like to answer in this video is what happens if a function takes a numpy array in input. The answer to this question is that it depends. To understand what can happen, consider this now familiar diagram that we have used to understand variables, arrays, and functions. As discussed at length, arrays are introduced once we recognize that instead of having one label for each individual thing that is being stored, we can have a single label to refer to multiple things as shown here. We can then use square brackets to refer to the position of the particular element of the array that we would like to access. Now suppose that we have a function such as the one in the green box shown here. The argument b that is passed to this function is clearly supposed to be a scalar, i.e. one thing. What happens if we write a function call such as the one shown at the bottom of the slide here, where we're passing an array rather than a single number? The answer to this thing is that the obvious thing happens. In essence, the scalar function is evaluated for each element in the array as shown here. In other words, if within the function the argument is treated as if it is a scalar, and if the function returns a scalar, then if the function is called using c equals func a as shown here, c is set equal to a scalar if a is a scalar, and c is an array with n elements if a is an array with n elements. To understand this in yet another way, consider the function definition and call shown on this slide here. The definition is shown up here. The argument that is passed to this function, x, can be a scalar or a numpy array. When the function x2 is called on this line, however, the input argument xv is a numpy array, and as such, yv is a numpy array with the same number of elements as xv. Notice that on this slide I have used a function that is part of the numpy library, namely np linspace, when I set up xv. This function takes 3 arguments. All the elements in the array that is generated are greater than or equal to the first argument, 0 here, and less than or equal to the second argument, 5 here. The resulting values in the numpy array xv all fall within the range that is shown at the bottom of the slide. The final argument in the call to np linspace, 6 here, is the number of elements that will be in the final array that is created. These 6 values are equally spaced between the lower and upper bounds that were given in the first 2 arguments, as shown here. Notice that as the first element of the resulting list, xv, is equal to the lower bound, and the last element in the list is equal to the upper bound, the spacing between the points is equal to the expression shown here. For the command that was used to generate xv, for instance, the spacing is 5 divided by 5, i.e. 1. One final thought about the code on this slide. This is the code required to generate the data that could be plotted to draw a quadratic. By using these functions that take numpy array as input, we can generate a graph of a quadratic function without using a for loop, which, yet again, reduces the amount of code that we are writing and thus reduces the number of bugs that there will be in our program. Before I finish, I want to remind you that I said what happens if a function takes a numpy array and input depends on what the function does. To consider why, look at the code on this slide. Even though xv is an array created with the np linspace command that we have just learned about here, yv is a scalar and not an array. The reason is that sum is adding up all of the elements within the array as shown here. Importantly, the input argument xv here is treated as if it is an array within the function, as it makes no sense to calculate the sum of a single number. What the function does with its arguments thus depends on what is done internally within the function. If within the function you treat an argument as if it is an array, then by referring to individual elements within the array using the square brackets access, for instance, then it will do one thing. If, however, the argument is treated as if it is a scalar, it will do something different. In other words, and to summarize, if a Python function expects a scalar and you pass it a numpy array, a numpy array is returned containing the elements of the input array transformed by your scalar valued function. This is what happens in the code shown here. For this reason, the variable yv is a numpy array containing the squares of 0, 1, 2, 3, 4, and 5. There are times, however, when you write functions where the return value depends on all the elements in the numpy array. The example that we looked at in this video was the function sum. You can recognize such functions as it generally makes no sense to call them using a scalar valued input. Hopefully, the exercises will help you to understand this distinction a bit better. So, good luck.